What do we do with a story when the facts are real, but the meaning refuses to sit still? Science is often described as a lantern. It pushes back the dark one measured discovery at a time, naming forces, weighing particles, giving shape to the invisible. For centuries, that lantern has illuminated a comforting picture of reality. Causes lead to effects, time moves forward, matter obeys rules, and the universe, however vast, remains legible to a patient mind. It is a beautiful promise. It is also perhaps an incomplete one, because every so often, in the quiet machinery of a laboratory, something happens that does not fit the script. A result appears that seems less like an answer than a disturbance. An instrument records what should not be possible. A pattern emerges, then disappears. An equation predicts one kind of world, while an experiment whispers another. And for a brief moment, the floor beneath certainty feels thin. This is not a story about magic, nor about secret worlds hidden behind locked doors. It is a story about the edges of knowledge, where human beings encounter phenomena so strange that language itself seems to hesitate. It is about researchers who set out to measure one thing and found themselves staring at another, about light that behaves like memory, about emptiness that may not be empty, about connections that seem to ignore distance, and systems that challenge the neat border between observer and observed. What makes these moments enduring is not merely that they are puzzling, it is that they expose something intimate about us. We do not fear mystery because it is dark. We fear it because it is familiar. Each anomaly reminds us that the universe is not obligated to resemble our intuition. And so we begin there, in that uneasy gap between what we can test and what we can truly comprehend. Not with certainty, but with attention. Not with conclusions, but with a question. When reality resists the stories we tell about it, do we revise the story or ourselves? What if the strangest revolutions in science began not with certainty, but with a flicker on a screen no one expected to see? At the end of the 19th century, physics appeared almost complete. The great structures were standing. Newton had explained motion, Maxwell had unified electricity and magnetism, and many believed the remaining work would be little more than refinement. The universe, it seemed, had settled into order. Then, in 1895, Wilhelm Conrad Röntgen was working alone with a cathode ray tube in a darkened room. He had covered the apparatus, trying to keep its glow contained. Yet across the room, a fluorescent screen began to shimmer anyway. Something invisible was passing through cardboard, through air, perhaps even through the ordinary confidence of the age itself. Röntgen did what careful minds do when the world behaves oddly. He stayed with the anomaly. He tested books, wood, metal, and finally the bones in his wife's hand. The image that emerged was both clinical and intimate. Flesh became a veil. Inside the familiar human body lay a ghostly architecture of fingers and rings and silence. It is difficult now, in an age saturated with imaging, to recover the shock of that moment. For the first time, human beings could look beneath the skin without a blade. A hidden interior had been made visible by a force no one had properly imagined. It was medicine, certainly, but it was also philosophy. If nature contained rays that could slip through matter as though solidity were only a partial truth, then what else had been moving around us unnoticed all along? The discovery of X-rays did more than open the body. It opened a deeper cultural wound in the story of certainty. The world was no longer limited to what human senses had evolved to perceive. Reality was broader, stranger, and less obedient to intuition than anyone had comfortably assumed. And that may be the real beginning of modern wonder. The moment we realize that the invisible was not empty, only waiting for a different kind of vision. If one hidden layer could suddenly reveal itself, how many others still lie just beyond the reach of our confidence? How do you measure light when light refuses to behave like a single thing? By the early 20th century, light had already unsettled centuries of certainty. It had been described as a wave, elegant and continuous, spreading through space with the grace of ripples across water. That picture explains so much that it felt nearly complete. But in 1905, a quieter and more troubling possibility emerged. What if light also arrived in packets, discrete bursts that behaved less like a smooth wave and more like tiny acts of delivery? The puzzle came into focus through the photoelectric effect. When light struck certain metals, electrons were knocked free. At first glance, the phenomenon seemed simple, but the details were wrong in all the right ways. Brightness alone could not explain the result. A dim light of high enough frequency could trigger release, while a brighter light of lower frequency could fail entirely. It was as though light carried not just intensity, but a kind of threshold message. Albert Einstein proposed that light came in quanta, later called photons. It was a radical thought, not because it discarded the wave picture entirely, but because it forced science to hold two conflicting truths at once. Light behaved like a wave in some experiments, like a particle in others, and completely like neither when pressed too hard for a tidy answer. This was more than a technical correction. It changed the emotional architecture of physics. Nature was no longer offering a single, stable face to observation. Instead, it seemed to shift depending on the questions asked and the instruments used. Reality did not become irrational, but it became less obedient to common sense. The photoelectric effect eventually helped build entire technological worlds, from solar cells to sensors to modern electronics. Yet beneath those practical triumphs remained a quieter unease. If light itself could not be confined to one identity, what did that say about the categories we rely on to feel oriented? Perhaps this is what discovery often does at its deepest level. It does not simply add knowledge. It asks us to become larger than the mental shapes we inherited. And if light can be both wave and particle, perhaps truth itself is sometimes wider than the forms we use to contain it. What happens when matter begins to flicker like possibility instead of substance? In 1927, deep inside the emerging world of quantum mechanics, a set of experiments with electrons began to erode one of the oldest assumptions humans have ever held, that objects simply are where they are. Fire a stream of electrons toward a barrier with two narrow openings, and you might expect each particle to pass through one slit or the other, like grains of sand through a fence. But the pattern that formed on the screen beyond told a different story. Instead of two clean bands, researchers saw an interference pattern, the signature of a wave. It was as if each electron had spread out, passed through both openings, and then interfered with itself before arriving. The result was strange enough. Stranger still was what happened when scientists tried to observe which slit the electron actually used. The interference vanished. The electron behaved like a particle again, as though the act of watching had changed the event itself. This was not mysticism, it was measurement colliding with the limits of classical thought. Quantum physics did not say that consciousness magically creates reality, but it did force a painful revision. Observation is not always passive. At the smallest scales, the tools of inquiry become part of the story they are trying to tell. The double-slit experiment endures because it feels less like a result and more like a mirror held up to the human mind. We want the world to be definite before we look. We want nature to possess clear answers independent of our encounter with it. Yet here was evidence that the boundary between event and witness was thinner than anyone had imagined. From that fracture came a century of argument, interpretation, and technological revolution. Quantum theory worked with astonishing precision, even as its meaning remained elusive. It could predict outcomes with extraordinary success, while refusing to say in ordinary language what was really happening beneath them. And perhaps that is why the experiment still haunts us. It reminds us that knowledge is not always the same as clarity. Sometimes we learn the rules long before we understand the reality they describe. When the universe acts differently under our gaze, the question is no longer only what we are seeing, it is also what kind of seeing is possible at all. Can emptiness have a weight, a texture, even a voice too faint for the ears but loud enough to alter matter? In the middle of the 20th century, physicists began asking an unsettling question about the vacuum, not outer space as a poetic backdrop, but vacuum as a physical condition, a region stripped as cleanly as possible of particles and noise. Common sense suggested such emptiness should be nothing at all, a blank, a pause between events. But quantum theory had already begun to hint that emptiness might be more active than it looked. Then came an effect so delicate it seemed almost philosophical. Place two metal plates extremely close together in a vacuum, and they will drift toward one another. No magnet pulls them, no visible force connects them, yet the gap between them is not truly empty. Quantum fields, restless even in their lowest state, fluctuate continuously. The plates change which fluctuations can exist between them, and that tiny imbalance creates a measurable push. This became known as the Casimir effect, and its importance reaches far beyond the apparatus itself. It suggests that what we call nothing may be a sea of hidden activity, a background trembling with unrealized events. The vacuum is not a void in the old sense. It is more like a stage before the actors enter, already charged with tension, already carrying the possibility of form. For science, this was not merely a curiosity. It was another fracture in the classical picture of reality. Matter no longer stood apart from emptiness as though substance and absence were opposites. Instead, the line between them softened. What appears vacant may still shape the world. What seems silent may still exert influence. There is something deeply human in that idea. We often imagine meaning as something obvious and solid, something visible enough to hold. But nature keeps proposing another model. Sometimes the unseen does not merely surround the visible. It helps create it. So the vacuum, once imagined as the simplest thing in existence, became one more reminder that simplicity is often a story told too soon. And if even emptiness is alive with hidden structure, then perhaps the universe is less a collection of objects than a conversation between presences we notice and presences we almost miss. What does distance mean if two things can remain linked after the world has pulled them apart? In 1935, a paradox arrived like a splinter in the mind of physics. Albert Einstein, along with Boris Podolsky and Nathan Rosen, pointed to a consequence of quantum theory they found deeply unsettling. If the equations were taken seriously, then two particles that once interacted could become entangled, their properties bound together in a way that survives separation. Measure one here and the other, far away, seemed to answer instantly. Einstein disliked the implication. He called it, with a mixture of wit and discomfort, spooky action at a distance. The phrase has survived because it captures the emotional core of the problem. Classical intuition depends on separation. One object is here, another is there, and influence moves between them through space over time. Entanglement seemed to ignore that choreography. For decades, the issue lingered as a philosophical wound. Then experiments, refined across the late 20th century, began to close the loopholes. Again and again, nature sided with quantum mechanics. Entangled particles displayed correlations too strong to be explained by any simple hidden script written in advance. Something in the universe was more relational than physics had once allowed. This did not mean messages were traveling faster than light in any ordinary sense. The mystery is subtler than that, and perhaps more profound. Entanglement suggests that under certain conditions, reality cannot be fully described as a collection of separate parts. The whole carries information the pieces do not contain on their own. Connection is not merely something added afterward. Sometimes it is fundamental. That insight reaches beyond the laboratory. Human beings also live by the fiction of clean separation. We imagine ourselves as self-contained, neatly bounded by skin and biography. Yet memory, grief, love, and history rarely obey those borders. We affect one another across time and distance in ways that cannot always be measured, only felt. Quantum entanglement is not a metaphor for human intimacy, but it invites one. It asks whether the deepest truths of the world may be less about isolated things than about relationships that persist even when visibility fails. And if that is so, then perhaps distance has never meant quite what we thought it did. What if time itself begins to lose its sharp edges the closer we look? In the world of ordinary experience, time feels dependable. It arranges life into before and after, gives memory its direction, and lets cause appear to march cleanly toward consequence. We build our days around that flow. We trust it without noticing how much of our sanity depends on the trust. But in the microscopic realm, physics has repeatedly suggested that time may not be the simple current it seems. One of the quietest disruptions came through experiments involving unstable particles and quantum decay. In the classical imagination, decay sounds like a clock hidden inside matter, a predictable countdown toward transformation. Yet quantum systems do not always die on schedule in that intuitive way. Left unobserved, they evolve according to probabilities. Under repeated measurement, however, that evolution can change. In some cases, frequent observation appears to slow the transition itself. This became known as the quantum Zeno effect, named after the ancient paradoxes of motion and stillness. The idea is unsettling in its simplicity. Watch a system often enough, and you can inhibit its change. Not forever, not by magic, but measurably. A particle, an atom, a fragile quantum state can linger longer than expected under the pressure of repeated checking. It is important not to overstate the mystery. No one is freezing time with a glance. The effect arises from the mathematics of quantum evolution and measurement. Yet even in its proper scientific frame, it disturbs the old confidence that processes unfold independently, untouched until we arrive to inspect them. Once again, observation is not merely a window. It becomes part of the weather. There is something almost painfully recognizable in that. Human life too changes when watched. A child under scrutiny behaves differently. A memory retold too often hardens into performance. Attention can preserve, but it can also interrupt the natural movement of becoming. The act of holding still for understanding sometimes alters the thing being understood. So the question grows deeper. If time at small scales can hesitate under inquiry, what does that say about the world we think we inhabit so effortlessly? Perhaps time is not a single river after all, but a layered experience, smooth from a distance and troubled up close. And perhaps the closer we come to truth, the more we discover that even change has conditions. What can we call a thing that exists and yet refuses to be touched without being changed? In 1935, Erwin Schrödinger offered a thought experiment that has since outlived countless textbooks. A sealed box, a cat, a tiny quantum trigger, and a cruel question about whether something can be both one thing and its opposite until observation resolves it. The image was deliberately absurd. Schrödinger was not trying to celebrate quantum mechanics. He was exposing how strange its logic seemed when carried from atoms into the familiar world. The puzzle was never really about the cat, it was about superposition, the idea that a quantum system can inhabit multiple possible states at once until measurement forces a definite outcome. At the microscopic level, the mathematics worked with astonishing success. But translated into ordinary life, it sounded almost intolerable. We do not live among half-open doors of reality. We do not wake each morning believing the kitchen table is both present and absent until we look. And yet the deeper science only sharpened the discomfort. Over time, experiments with increasingly complex particles and systems showed that superposition is not just a mathematical convenience. Under the right conditions, nature truly does preserve multiple possibilities at once. The problem is that the everyday world is noisy. Interaction with the environment rapidly destroys these delicate quantum states through decoherence, giving rise to the solid-seeming reality we know. That explanation helps, but it does not fully soothe the philosophical ache. It tells us how the world becomes classical, not why possibility must collapse into a single experience at all. Somewhere between the trembling ambiguity of the quantum world and the firm surfaces of daily life, the universe seems to choose. Or perhaps choice is the wrong word, and what we call certainty is simply the shape left behind when fragile alternatives can no longer survive. There is a human resonance here that is hard to ignore. Much of life unfolds in superposition long before action gives it form. A future remains many futures until a decision is made. A memory contains several meanings until one settles into identity. Possibility is often richer than outcome, even as outcome is the only place we can live. So Schrödinger's box remains with us not because it is bizarre, but because it is intimate. It asks whether reality is fundamentally made of settled facts, or whether facts are only the final residue of possibilities we were never fully equipped to witness. What if the laws of physics are not broken by chaos but revealed through it? For generations, classical science carried an implicit promise. If we knew enough, we could predict enough. The universe might be complicated, but underneath that complication lay order, and order meant control. Then came the strange beauty of systems so sensitive that even the smallest uncertainty could grow into overwhelming divergence. Not disorder without rules, but order so intricate it began to resemble mystery. This realization emerged across many fields, from weather to fluid dynamics to population biology. Tiny variations in initial conditions, once dismissed as trivial, proved capable of reshaping entire outcomes. A fraction of a degree, a slight fluctuation in pressure, a nearly invisible difference at the start could unfold into dramatically different futures. Determinism remained in one sense intact, yet prediction became fragile. The rules were stable, While the outcomes slipped beyond practical reach, chaos theory did not overthrow physics. It altered its emotional tone. It suggested that uncertainty is not always a sign of ignorance waiting to be cured. Sometimes it is woven into the scale and complexity of the world itself. Even when the laws are known, the future may remain partly veiled, not because nature is irrational, but because precision has limits and time amplifies every imperfection. There is something humbling in that. Human beings often mistake explanation for mastery. We believe that once a mechanism is named, the world has somehow become safer. But chaos reminds us that knowledge can coexist with unpredictability. A storm may obey equations and still remain resistant to exact foresight. A heart may follow biological laws and still surprise itself. In that sense, chaos is not the enemy of reason. It is reason stripped of arrogance. It teaches that truth is sometimes less like a straight road and more like a branching river, where every current is lawful and yet no final shape can be entirely secured in advance. Perhaps this is why chaos feels so strangely familiar. Our lives, too, are built from tiny beginnings whose consequences we only understand in retrospect. A missed train, a chance meeting, a sentence spoken at the wrong moment. So much of what defines us begins as something almost too small to notice. And maybe that is the deeper lesson. The universe does not have to break its laws to remain profoundly, permanently beyond our complete control. What do we make of a universe that seems to remember more than our theories first allow? In laboratories built for precision, scientists have often discovered something more elusive than data: persistence. Certain systems, once disturbed, do not simply return to silence. They carry traces. A magnet retains alignment. A crystal preserves the story of pressure and heat. Even at the edge of quantum behavior, researchers have found that the past can linger in ways that complicate our neat distinction between event and aftermath. One pathway into this mystery came through the study of hysteresis and memory effects in physical materials. Change the conditions around a system, then restore them, and the system does not always come back unchanged. It may follow a different path home. The present depends not only on current forces, but on the route by which it arrived. Matter, in this sense, becomes historical. That idea may sound modest beside the grand strangeness of quantum theory, yet it quietly alters the emotional logic of physics. We often imagine nature as immediate, governed by the now. But memory enters even here, not as consciousness, not as intention, but as structure shaped by what has already happened. The world is not only reacting, in some sense it is retaining. Modern research has extended this intuition into increasingly subtle domains. In condensed matter systems, in complex materials, and in certain quantum experiments, history matters. The same input does not always yield the same output if the journey differs. A system may encode previous states in ways that remain hidden until the right condition draws them out. The present becomes layered, carrying shadows of earlier arrangements. There is a profound human familiarity in that. We too are historical creatures. No conversation begins at zero. No grief arrives untouched by old losses. No joy is free of memory's undertow. What we call identity is often less a fixed essence than a record of passages endured. Physics does not sentimentalize this. It simply reveals again and again that the universe is not built from isolated moments alone. Events accumulate, paths matter, traces remain, and perhaps that is why these experiments feel so intimate. They suggest that reality is not merely a sequence of instants, but a fabric in which earlier states continue to press gently against the present, asking whether anything truly vanishes once it has been real. What if the most important discoveries are the ones that show us how little the senses were ever designed to know? By the late 20th century, physics had become a discipline of instruments as much as ideas. Human perception, once the starting point of inquiry, was no longer enough. We had built machines to hear the faint tremor of space-time, to detect particles that exist for less than a heartbeat, to map radiation older than any star now living. Each device extended the body. Each one also humbled it. One of the clearest examples came from the search for the cosmic microwave background and the strange irregularities hidden inside it. What first appeared as static, a faint and nearly uniform afterglow spread across the sky, slowly revealed itself as a record of the early universe. Tiny temperature variations, unimaginably subtle, contain the seeds of galaxies, clusters, and all the large-scale structure that would follow. Noise became memory, background became. This transformation depended on a radical shift in attitude. Scientists had to learn that what looks insignificant may carry the deepest story. A blur in the data, a fluctuation once dismissed as error, can become a map of creation if seen with enough patience and enough care. The experiment does not only measure the universe, it teaches us how to notice differently. That lesson repeats across modern physics. Gravitational waves arrive first as almost impossible whispers. Neutrinos pass through Earth by the trillions, mostly untouched and unnoticed. Dark matter announced itself only through its absence, by the gravity of something never directly seen. Again and again, reality has expanded not because the world changed, but because our methods of listening became more refined. There is something quietly moving in that progression. It suggests that truth is not always hidden behind walls. Sometimes it is present all along, woven into the ordinary field of experience, but pitched beyond the range of our inherited senses. Discovery, then, becomes less an act of conquest than one of tuning. And perhaps that applies to more than science. Much of life is shaped by signals we fail to recognize until time, grief, or love adjust the instrument. The overlooked sentence, the background sorrow, the small kindness that changes a life. If the universe speaks most deeply in faint frequencies, maybe wisdom begins when we stop demanding loud proof and start learning how to listen. What happens when the closer we come to explaining everything, the more clearly we see the outline of what still escapes us? By the beginning of the 21st century, physics had become both triumphant and uneasy. Its equations could predict phenomena with astonishing accuracy. Its technologies had reshaped civilization, and yet the deeper the discipline reached, the more often it encountered absences that refused to disappear. Dark matter seemed to hold galaxies together without revealing its face. Dark energy appeared to drive the expansion of the universe while remaining almost entirely unnamed. The map had grown vast, but large territories were still marked by shadows. This was not failure in the ordinary sense. It was something more interesting and more difficult to live with. The better science became, the more precisely it could measure the scale of its own incompleteness. Each solved puzzle sharpened the next mystery. Each new instrument widened the horizon, and with it, the perimeter of the unknown. Knowledge did not close the circle. It enlarged it. There is a temptation when confronted by such limits to imagine that certainty lies just one breakthrough away. Perhaps it does, but history suggests a more humbling pattern. Every generation believes it stands near the end of confusion, only to discover that clarity opens into a deeper kind of complexity. The universe does not merely keep secrets. It changes the very meaning of the questions we ask. In that sense, modern physics has become a study not only of matter and energy, but of intellectual maturity. It asks whether we can remain devoted to truth without demanding that truth becomes simple. It asks whether understanding must always culminate in closure, or whether some of the most honest knowledge arrives as disciplined wonder. That may be the quiet dignity of science at its best. Not that it eliminates mystery, but that it teaches us how to meet mystery without surrendering to fantasy, to remain exacting, careful, and open, to say with equal seriousness, this is what we know, this is what the evidence allows, and this is where the darkness begins again. And if the unknown continues to recede as we approach it, perhaps that is not the sign of a broken quest. Perhaps it is the mark of a living universe, one that keeps inviting us forward not with final answers, but with deeper and more beautiful forms of attention. What remains after all the experiments, all the equations, all the careful attempts to pin the universe to a page? A strange pattern begins to emerge when we look back across these moments in physics. Again and again, the great disturbances did not arrive because nature was chaotic or deceptive. They arrived because human expectation was too narrow. We assumed matter was solid, then found it porous with uncertainty. We assumed emptiness was blank, then discovered it seething with activity. We assumed distance guaranteed separation, then watched correlations survive the gap. Each surprise was in its own way a correction not only of theory but of temperament. That may be why these experiments continue to resonate beyond the laboratory. They are not merely technical milestones. They are encounters with humility. Each one reminds us that the universe is under no obligation to arrange itself around the scale of human intuition. We evolved to throw stones, read faces, survive winters, and remember paths home. We did not evolve to naturally grasp quantum fields, warp space-time, or the deep history written in background radiation. And yet we have reached for them anyway. That may be the most remarkable fact of all. A species shaped by hunger, fear, tenderness, and time has built instruments capable of detecting whispers older than the earth. We have argued with reality, revised our metaphors, and continued forward even when the answers made the world feel less familiar than before. There is courage in that kind of attention. The story of broken expectations is, in the end, not a story of defeat. It is a story of enlargement. Every unsettling result has widened the frame in which human thought can move. We are less certain, perhaps, than earlier ages imagined themselves to be. But we are also more awake to complexity, more honest about ambiguity, and more capable of wonder without illusion. So perhaps the real legacy of these experiments is not that they shattered physics, but that they deepened it. They turned science from a search for simple certainty into something wiser, a disciplined conversation with a reality that exceeds us, yet still allows itself to be known in fragments. And maybe that is enough. Maybe truth was never meant to be possessed, only approached with patience, rigor, and awe. In the end, what do these experiments leave us with besides data, diagrams, and a longer archive of astonishment? They leave us with a different image of ourselves, not as masters standing above the universe, but as participants within it, listening from inside the mystery rather than outside it. The deeper physics has gone, the less the world has resembled a machine built for easy reading. It has become something subtler and more intimate, a reality layered with hidden structures, provisional appearances, and meanings that emerge only through patience. What once seemed solid has become dynamic. What looked empty now trembles with possibility. What felt certain has learned to speak in probabilities, relations, and traces. And yet none of this diminishes the human story. It enlarges it. Because every one of these discoveries began with a person noticing something small and refusing to look away. A flicker on a screen, a pattern in noise, a result that did not belong. Science at its best is not cold accumulation. It is disciplined curiosity shaped by humility. It is the willingness to let the world correct us, even when correction comes at the cost of comfort. That is why these moments matter beyond physics. They remind us that understanding is not the same as control, and that uncertainty is not always failure. Sometimes uncertainty is the most faithful response to a reality still unfolding beyond our tools, our metaphors, and our current reach. To live honestly with that fact is not weakness. It is a form of maturity. We often speak of truth as though it were a destination waiting at the end of inquiry. But perhaps truth is also a relationship, something that deepens as we become more careful in how we ask, how we test, and how we listen. The universe may never become fully familiar to us. There may always remain regions of darkness, not sinister, simply beyond the circle of present light. And maybe that is the final human insight these experiments offer. Not that knowledge will end mystery, but that mystery itself can be a kind of invitation. To stay curious, to stay rigorous, to remain tender before what exceeds us. In that sense, the future of science is also the future of wisdom, not the conquest of the unknown, but a deeper companionship with it.